Hello everyone, a very good evening to all. I welcome you all once again for this fourth interaction session on the course Experimental Physics 1, which is being flowed this July 2025 session by NPTEL with course code NOC 25 PH 51. I am Vivekananda Nayak. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today we will be discussing a few sample problems from the course content of week 4 lectures, and we will mainly cover problems related to Young's modulus of how to calculate Young's modulus of elasticity and the problems related to Young's modulus of elasticity and error analysis, which is a part of basic analysis like we discussed in the last introduction session. Some of the basic analysis part is performing experiments, then data plotting, error analysis, calibration, and all. So we will let's first discuss a few things about error analysis, and then we will move towards solving the questions. So if you talk about the error analysis, what is error analysis? The process of evaluating the uncertainty associated with a measurement result is often called uncertainty analysis or error analysis. So this is the process of evaluating the uncertainty associated with a measurement. So what is uncertainty? For example, suppose you have a meter scale. So in that meter scale, the suppose let's take a small scale. Suppose take a small example. So this is a meter scale, and the least count is 1 millimeter. But if you are measuring something, uh, and you need more accuracy, you can't get that accuracy with this 1 millimeter least count scale. So there some uncertainty comes into picture. So if you are doing a measurement, so what is measurement? The measurement is the best estimate plus minus the uncertainty in the measurement, then the units. So if you talk about the uncertainty, then the concept of accuracy and precision comes into picture, and the uncertainty is estimated associated with the measurement should account for both the accuracy and precision of the measurement. So this uncertainty basically gives an idea about the accuracy and precision of the measurement. So when the measurement is accurate, then we will be having less uncertainty, and when the measurement is precise, then we have very less uncertainty. For example, the order of the terms, like the number of significant figures we are discussing, so we can measure the smallest values, so that can be called as more precise measurement. So basically precise indicates the quality of the measurement. For example, we are measuring up to 4 decimal points or 5 decimal point, which is more precise than that of the case where we are measuring up to 2 decimal point. But that doesn't guarantee that the measurement is correct, because it might be wrong due to some other factors. And accuracy is the case where the measurement, the output you are getting by the measurement, which is close to the actual value. That is, assumes that there is an ideal value and how far your answer is from that ideal right value. So accuracy means which is how close are your results corresponding to a particular known value. So you can understand accuracy and precision from this figure. So here you see, so accurate means, so you know this yellow part is 10. So if you are hitting close to the yellow part, then this is accurate. But in case of precise, you are not hitting this yellow part, but where you are hitting for multiple times, you are getting that value. So you are making precise measurements, but the measurements are not accurate. So these are the case where this is accurate and precise. That is, you are getting correct values, and when you are repeating the experiments, you are again and again getting the repeated results. So this is accurate and precise. Now these results you are getting precise values, but it is not accurate because it is not at the desired center value. And again, this case, it is accurate but not precise, so it is close to the actual value, but we are getting some different results each time we are measuring the performing the experiments. And here it is not accurate and not precise, so neither it is close to the exact value, known value, or the results are being repeated. And these are the some of the sources of error. For example, you incomplete definition, failure to account for a factor. For example, if you are measuring something and there are different factors that are affecting that measurement, and if you don't take into account those factors, then your measurement will be affected. And this is environmental factors. For example, you want to measure the temperature of this room, so that might be different depending upon the environment you are in. So if it is another case, then instrument resolution, which is again related to the least count of the measurement. Then calibration. So calibration is basically the measurement you are taking. You are using certain instrument, whether that instrument is calibrated. For example, suppose you are measuring the room temperature and you are using a thermometer, and you found that the actual reading you are getting is 35 degrees Celsius. But how do you know the 35 degrees is correct? So you should have some reference temperature where the known value of the temperature and the measurement you are doing, and you are getting the same value. So you need to calibrate your instrument in order to measure the accurate value. Then another is zero offset. So zero offset we have discussed in case of slide calipers and vernier and screw gauge we discussed in the initial sessions. So when there is zero offset is present, so there will be zero error, and that zero error is also one of the cause for the error in the measurement. Then there is physical variation, parallax error, drift instrument, lag time and hysteresis, and personal errors. So these are different sources of error. And if you mainly discuss the types of error, there are three types of error. One is illegitimate errors or gross error, which originate from the mistake or blunders that is being performed, that is made by the person measuring the person doing the experiment, or some steps in the measurement. For example, if you want to measure the amount of liquid you have in a container, and during that measurement, when you are pouring the liquid from that larger container to your measuring jars, then some of the liquid are getting spilled out of the container. Then in that case, these are again some part of the error, and you will not get the actual value. So these are the examples of gross error, illegitimate error. Then another is systematic errors present in all data points throughout the measurement. So in some cases, like that zero error or zero offset. So when you are, for example, we are measuring the weight of some substance by using uh, weighing machine. But that machine, we are using two-sided machine. So one side we are presenting some weight, or we are keeping some weight, and then the equivalent weight we are measuring. But if the two sides are not equal, and there is some value, or there is some difference between the two sides of that bar, then that value will always be present in all data points. So this is this is called as systematic error. Then other is random errors or residual errors that occurs randomly, though, and also that results in different measurement values on repetition. For example, you are uh, throwing a ball, and you are measuring the distance that ball travel. So if you are applying different forces, then according to your the force you are applying, the distance traveled by the ball, that will change. And another case, suppose the ball is not that heavy, the direction of wind will also affect the distance that the ball is traveling. So in one case, if the wind direction is opposite to the direction you are throwing, then in that case the ball will not travel that much distance. But when the wind is flowing along the direction of the ball you are throwing, then the ball will move to a larger distance. So in that case, these are the errors that will result in different readings when we are measuring something. So these errors can be minimized by, so how to minimize the errors? By improving the experimental procedure, removing personal bias, and using proper instruments. So using proper instruments and doing the experiment correctly are the ways to minimize the errors. And these are the formulas how the error propagates. So you know error is always getting added. So for whether it is sum or difference, the error will get added, because in each case the error is so if you are once you measure something and you found some error and again you are measuring something you found some error, so whether you subtract those things or add those things, error will always get added because you have error, so error is always increasing. So for multiplication and division, these are the formulas. This is the formula for power of a quantity. So when q is x to the power n, then if you take the log of it, then it will get del q by q, the relative error. And then this is if q is a function of x and y, then these are the formula for calculating the error value. So now let's discuss the first problem of our today's interaction session. The question says, in an experiment, the percentage error occurred in the measurement of physical quantities A, B, C, and D are 1%, 2%, 3%, and 4% respectively. Then the maximum percentage error in the measurement of Y. So this is given as maximum percentage error. So the maximum percentage error in the measurement of Y, where Y is a square B divided by CQ root D will be. So options are option A 5%, option B 10%, option C 15%, and option D 20%. So we have four. We are measuring a quantity. For example, we are measuring Y, and that Y is a function of four quantities A, B, C, and D. So A, B, C, and D. So the percentage error in D is 1%. In A is 1%. That means del A by A into 100 is 1%. So each time we are measuring the value of A, because first we will measure A, B, C, D, and then we will calculate Y. So when we are measuring A, the uncertainty in measurement of A is 1%. Then similarly for B it is 2%. That is the delta B by B into 100 is 2%. This is 3%. Delta C by C into 100 is 3%. Then 4%. Delta D by D into 100 equal to 4%. So these are the informations that we have been given in this problem, and we want to calculate the maximum percentage error of the quantity Y, where Y is expressed as Y is equals to A square B divided by CQ d to the D half. So what is the percentage of error in measurement of Y? So I'll give you a few minutes to solve this question, and then we will discuss what will be the correct answer. So here in this question it is mentioned, then calculate the maximum percentage error. So what we will do? So the expression for y is given as y equals to a square b divided by cq root d. So if you take logarithm, so taking the logarithmic differentiation, will get del y by y equals to a square. So 2 del a by a plus del b by b plus 3 del c by c plus, because it's 2d, it's d to the power half, so half del d by d. So what will be the percentage error? So percentage error will be del y by y into 100% equals to 2 del a by a into 100% plus del b by b into 100% plus 3 del c by c into 100% plus half del d by d into 100%. So if you calculate y by y into 100% will be 2 into del a by a, we know it is 1 plus del b by b is 2 plus 3 into del c by c is 3 plus half into 4 percentage. It is 2 plus 2 plus 9 plus 2 into percentage. So it is 15%. So maximum percentage error in the measurement of y is 15%. So the correct answer is option C. So I hope this is clear to everyone. Now we'll move to question number 2. Question number 2 says the ratio of the lengths of two wires A and B of same material is 1 is to 2 and the ratio of their diameters is 4 is to 1. They are stressed by the same force, then the ratio of increase in length will be, options are option A 1 is to 2, option B 4 is to 1, option C 1 is to 8 and option D 1 is to 32. So here the question says the ratio of the length of the two wires A and B are of the same material. So we have two wires A and B. Suppose this is A, this is B. The ratio of the length of the two wires of the material is 1 is to 2. So suppose A has length x, B is 2x. So let's make B larger. So this is B and this is A. So we have two wires and the length are in the ratio 1 is to 2 and their diameters is 4:1. So the A is thick and B is thin. So the ratio is, you take the ratio. So this is suppose 4y and this is y. Now they are stressed by the same force. So we are applying force. So we are applying force F here to stretch it, and also here to stretch the wire. Then what will be the ratio of increase in length? Then it will be elongated by some length and it will be elongated by some length, and we need to find out the ratio of these two. So I'll give you a few minutes to think about this question and to solve how we can solve it, and then we will discuss what will be the correct one. So now this question is related to the modulus of elasticity, because when you are applying force, the wires will be stretched, and the relative change in the length will only be calculated by using the concept of modulus of elasticity. And since we are talking about the case of wire, where the change in radius is not that, because for wires the assumption is the radius is very small as when compared to its length. So for this type of materials, the modulus of elasticity is called as Young's modulus of elasticity. So what is the formula for Young's modulus of elasticity? So here the ratio of increase in length. So the Young's modulus of elasticity Y is given by, so in general the modulus of elasticity is given by stress by strain. So stress is F by A, force applied per unit area, and strain is relative change in the dimension, like here the change in length by original length, delta L by L. And if you talk about the unit is Pascal, because the denominator term has no unit, length by length. So the unit of Young's modulus of elasticity is equal to the units of stress, and stress is also called as pressure. So the unit of Young's modulus of elasticity is Pascal. So now let's calculate. I will calculate. So one thing we should keep in mind: the uh, two wires are of same material. So if the material is same, the Young's modulus will be same only. So for both the cases, the Young's modulus will be same. So let's we need to find out the change in the ratio of the change in length of the two wires. So from this formula, what we got, y equals to F divided by A delta L by L. So what will be the change in length, or delta L? So delta L by L will be F by A divided by Y. So delta L will be F by A divided by Y into the length. Now this is equation 1. So let's arrange it again. So delta L equals to F L divided by AY. So now this is the working formula for this problem. So now let's find the case for two wires. So this is delta L. So the ratio of two wires, delta L A by delta L B, will be F A by F B into L A by L B. It will be A by AB into YA by YB. So this will be the ratio. Now in the question it is mentioned they are stressed by the same force and the same material. So same force, so FA by FB equals to 1, since the two materials are same, so for same material YA by YB will be 1 because Y is same for both the materials because the materials are same. Now delta L A by delta L B will be equals to L A by L B. So L A by L B is 1 by 2, it was given in the question. Then A by AB, A by AB, and area we know for a wire. This is the cross section. So this is R. So area is pi R square. So A is directly proportional to R square. So we can write here half into RA square divided by RB square. So half into RA by RB. What is the ratio of the radius? So the ratio of the radius, sorry, and the ratio of their diameters is 4 is to 1. So the if the diameter is 4 is to 1, the radius is also 4 is to 1. So it will be so 1 minute here. It is divided by A. So it is not into. So it is divided by. So it is 1 by 2 divided by 4 is to 1 square. So let me add another slide. So delta L A by delta L B will be 1 by 2 into 1 by 4 square. So 1 by 2 into 1 by 16 equals to 1 by 32. So delta L A is to delta L B is 1 is to 32. So the correct option is option D, 1 is to 32. I hope this is clear to everyone. So here, since the material is same, so the Young's modulus of elasticity will remain same, and the force applied is also same. So the change will depend upon the ratio of their length and ratio of the radius. So for area, the radius, the dependence of area and the radius is r square. So it will be, so since A it was in the denominator, A area, so it will be 1 by 2 divided by 4 square. So 1 by 2 into 1 by 16, it will be 1 by 32. So I hope this is clear to everyone. Now I'll move to question number 3. Question number 3 says A and B are two wires. The radius of A is twice that of B. They are stressed by the same load. Then the stress on B is. So these options are option A equal to that on A, option B 4 times that on A, option C 2 times that on A, and option D half that on A. So there are two wires. So A and B, the radius of A is twice that of B. So it is 2x and it is x. They are stressed by the same load. Then the stress on B is equal to that of A. So load is same. So they are being stressed by same load. Same load means the force applied on both is same. Then we need to find out the stress of B in terms of, sorry, the stress of B in relation to A. So this question is pretty much similar to the previous one. I'll give a few minutes to try this question and then we will discuss what will be the correct answer. So let's solve this one. So it is pretty much simpler than the previous one. So stress means stress A by stress B. We know stress is given by force per unit area. So it is F by A for A, F by A for B. So since they are stressed by the same load means FA equals to FB. So that implies SA by SB will be AB by AA. And again we know A is right proportional to R square. So it will be RB by RA square. And here it is mentioned that the radius of A is twice that of B. So radius of A is twice that of B. That means it is 1 by 2 square. It is 1 by 4. So the stress on A is equals to stress on B by 4, or the question says the stress on B. So the stress on B will be 4 into stress on A. So the correct answer will be option B, that is 4 times that on A, because the area of A is more. So since stress is inversely proportional to area, so the stress will be more on B and it will be less on A. So I hope this is clear to everyone. Now we'll move to question number 4. Question number 4 says A and B are two wires. The radius of A is twice that of B. They are stressed by same load. Then the stress is. So again this question, I think this question is getting repeated. So you don't need to solve this. Repeated question. Now I'll move to question number 5. Question number 5 says in an experiment, the percentage error occurred in the measurement of physical quantities A, B, C, and D are 4%, 2%, 1%, and 4% respectively. Then the maximum percentage error in the measurement of Y, where Y is A BQ divided by C square root D. So again, A, B, C, D, there are 4 variables. Error in A is 4%, in B it is 2%, in C it is 1%, and in D it is 4%. And the formula for Y is A BQ divided by C square root D. So what is the percentage of error in the measurement of Y? This is pretty much similar to the question that we solved at the beginning of the interaction session. So I'll give you a few minutes to try this and solve, and then we will discuss what will be the correct one. So this is question mark. So again, this is pretty much simpler. So y by y into 100% will be a by a into 100 plus 3 into db by b into 100 plus 2 into dc by c into 100 plus half into dd by d into 100. So percentage. So delta a by a. So a, the percentage error is 4%. So 4 plus 3 into 2 plus 2 into 1 plus half into 4. So total it will be 4 plus 6 plus 2 plus 2. So the correct answer is option A, 14%. I hope this is clear to everyone. Now let's move to question number 6. Question number 6 says, if the error in measurement of radius of a sphere is 3%, then the error in measurement in the volume of the sphere. Options are option A 3%, option B 6%, option C 9%, and option D 27%. So the error in the measurement of radius. So in radius measurement, the error is 3%, and the in the measurement of the volume. So in case of a sphere, volume is given by 4 by 3 pi r cube for sphere. So we need to find out what will be. So in case of radius, we have for radius r by r into 100 is 3%. Then suppose v is volume, so we need to find out del v by b into 100%. So this question is pretty much similar to the previous question that we are solving. Same type of procedure we can follow to get the answer. So I'll give you a few minutes to try this and then we'll discuss. So let's solve this one. So here, so this 4 by 3. So V is 4 by 3 pi r cube. So this 4, 3, pi, these are constants. So there will be no error because pi, we know the value, pi is 3.142 or 22.7. So pi, these values are constant. So only the variable that is the volume is dependent is rq. So if you take log and differentiate, take log, then differentiate, it will be b by b into 100% equals to 3 dr by r into 100%. So 3 into dr by 3, so it is 3%. So 9%. So the correct answer is option C, 9%. So I hope this is clear to everyone. Now we'll move to question number 7. Question number 7 says the period of oscillation for a simple pendulum is t 2 pi l by g square root. Measured values of L is 50 centimeter, known to 1 millimeter accuracy, and time for one oscillation of the pendulum is found to be 2.5 seconds using a digital watch of 1 millisecond resolution. So what is the percentage error in the determination of G? So this is somehow related to the previous questions, but this question is different. So here in this question it is mentioned that the time in an experiment they are calculating the time period of oscillation of a simple pendulum, where t is the time period of oscillation, L is the length of the pendulum, and G is the, sorry, L is the length of the pendulum and G is the acceleration due to gravity. So it is 2 pi L by G. So in general, what we do in the experiment, so the experiment name is to find out the value of G by using a simple pendulum. So when you measure the time and measure the length, then by putting the value, you can get the value of G. But here there are some error in the measurements. So here it is given. So the measured value of T, the value of T is 50 centimeter and with 1 millimeter accuracy, and the length of the pendulum is, sorry, the length is 50 centimeter with 1 mm accuracy, and the time T is 2.5 second, and the resolution is 1 millisecond. Basically it reflects the least count of the instrument that has been used to calculate, to measure. So in length we are using a 1 millimeter least count scale, and for time where it's measuring to time is being measured by a digital watch of 1 millisecond resolution. So we need to find out what will be the percentage error in the determination of G. So we have T equals to 2 pi L by G root over, that implies T square equals to 4 pi square L by G. G is 4 pi square L by T square. So if you take log and differentiate, the error will get added up to get most possible error. So dg by g into 100 equals to, again 4 pi square are constant, so it will be dl by l into 100 plus 2 dt by t into 100. And dl by l, so what will be dl by l? So l will be the length measured and dl will be the minimum length that can be measured, that is 1 mm. Then similarly t is 2.5 second and millisecond is dt is equals to 2 millisecond. 2 into, sorry, it is 2 mill, not 2 millisecond, it is 1 millisecond. It is so if you put the values, it will be 1 divided by, sorry, 1 mm means it is 0.1 centimeter, so it will be 0.1 because the limits will be same in numerator and denominator, sorry, units will be same in numerator and denominator, so it is 0.1 divided by 50 into 100% plus 2 into 10 to the power minus 3 by 2.5 into 100%. So when we calculate, dg by g into 100, it will be 0.1 into 2 plus 2 into 0.1 divided by 2.5. So 0.2 plus 0.08 is 0.28%. So the correct answer is 0.28%. So you see here the percentage error that we are getting in the determination of G is quite small. It is small because the measurements we are using that are more reliable. So when the overall length we are measuring is 50 centimeter and the least count is 1 millimeter, so the percentage of error in measurement of L is small. Again, the percentage of error measurement of T is even smaller because we are using a least count instrument of least count 1 millisecond. So the percentage of error is quite small in both L and T. So that's why the most probable error in the measurement, the most probable percentage error in the measurement of G, we are getting only 0.28%. But in the previous question, since the percentage error of the quantities involved in measurement is quite high, we are getting higher value of the percentage error in measurement of the quantity. So I hope this is clear to everyone. Now we'll move to question number 8. Question number 8 says percentage errors in the measurement of mass and speed are 2% and 1% respectively. The error in the estimation of kinetic energy obtained by measuring mass and speed will be. So Options are option A 4%, option B 2%, option C 10%, and option D 3%. So in the measurement of mass, suppose it is m, it is 2%. That means dm by m into 100% is 2%. For velocity, it is 1%. So dv by v into 100 is 1%. And here we need to find out the error in kinetic energy. So kinetic error. So error in kinetic energy will be how much? So I'll give you a few minutes to try this question, and then we will discuss what will be the correct answer. So we know the expression for kinetic energy is given by half mv square. Suppose we can write it as E is equals to half mv square. So again log and differentiate delta E by E into 100% will be, so half is constant, it will be dm by m into 100% plus 2 dv by v into 100%. So dm by m into 100% is 2%. So 2 plus 2 into 1, 2 plus 2, 4%. So correct answer is option A, 4%. So all these questions are pretty much similar to each other. Now let's move to question number 9. Question number 9 says, which of the following is true for elastic potential energy density, that is potential energy per unit volume? So these are the options. Option A, energy density equals to stress into strain. Option B, half stress into strain. Option C, stress into strain by volume. Or option D, this is option D, stress into volume divided by strain. So we need to find out the correct expression for elastic potential energy density, that is potential energy per unit volume. Potential energy per unit volume. So elastic potential energy, the formula is elastic potential energy is given as half into force into elongation. That implies half into F into small l. So now for unit volume, what we can write? Elastic potential energy per unit volume will be half into F into L by V. So that V can be written as F into L, A into L. So it will be half into F by A into small l by capital L. So F by A, we know this is stress and this is strain. So elastic potential energy per unit volume is equals to half into stress into strain. So the correct answer is half into stress into strain, that is option B. So I hope this is clear to everyone. Now we'll move to question number 10. Question number 10 says the ratio of radii of two wires of same material is n is to 1. The length of the wire are 5 meter each. On applying same load, the ratio of the increase in length of the thin wire to that of the thick wire is. Options are option A 2n is to 1, option B n is to 1, option C n square is to 1, or option D 1 is to 1. So pretty much similar types of question we have solved today, but here the ratios are different, that is n is to 1. So in previous questions there were some definite numerical values of the ratios, and here we need to find out the ratio of increase in length of the thin wire to that of the thick wire. So the length of the wire are 5 meter each, and we are applying same load. So same load F same, L same, length is also same, and the material is same material, that implies y is same. So only the radius is different. So what will be the ratio of increase in length of thin wire to that of thick wire? So suppose thin wire we will denote as small t, thick wire denote as capital T. So delta L, the length of thin wire to that of thick wire. So delta L small t divided by delta L capital T, that will be the answer. So I'll give you a few minutes to think about this question because it's quite uh, similar to the previous questions we have solved, and then we will solve to get the correct answer. So if you calculate it, we know y is equals to f divided by a small l by capital L. So small l is f l divided by a y. So L small t divided by L capital T is f l y into a y f l. So f is same. So f and l is same. Again y is same. So only it will depend upon the area, and we know a is right proportional to r square. It will be r t square divided by r small t square. That implies L small t by L capital T is n r square divided by r square, because here it is mentioned the ratio of two radii of wire is n is to 1. So for thin radius is 1, for thick radius is n. So n by r square, so it will be n square by 1. So LT is to L capital T is n square is to 1. So the correct option is option C, n square is to 1. So if the radius, if all other parameters are fixed, it is inverse proportional to the radius square. So if this is clear to everyone, I will move to question number 11. Question number 11 says, two wires P and Q of the same material have radii in the ratio 2 is to 1 and length in the ratio 2 is to 1. The ratio of the normal forces required to produce same change in length of these two wires is option A 1 is to 1, option B 2 is to 1, option C 4 is to 1, and option D 1 is to 4. So there are two wires P and Q. So same material, and radius are in the ratio 2 is to 1, length is also 2 is to 1, and we need to find out the normal force required to produce same change in length. So change in length same, and we need to find out the normal force. So what will be the Fp by Fq? This is the question. So it is a bit different. We need to find out the force so that the change in length will be constant. So here the variable, that the variable different. So I'll give you a few minutes to think about this question and try to solve it, and then we will discuss what will be the correct answer. So if we solve it, let's so again we know y equals to FL divided by AL. So F is equals to A Y small l by capital L. So here F P by F Q will be A P by A Q into Y P by Y Q L P by L Q into L Q by L P. So YP YQ it is 1 because Y is same, also the elongation is same, so this is also 1 because the elongation is same and the length and radius are different. So AP by Q is we can write R square P by R square Q into L Q by LP. So FP by FQ equals to, so radius is 2 is to 1, length is 2 is to 1. So it is 4 by 1 into 1 into 1 into 1 by 2. Because for length it is Q by P, but for radius it is P by Q. So it is 4 by 1, it is 1 by 2. That is 2 by 1 square, or it is 1 by 2. So if you, it will be 2 by 1, that is 2 is to 1. FP is to FQ. So in order to produce similar elongation or the same elongation between in wires P and Q, the force that should be applied should be in the ratio of 2 is to 1. So this is the correct answer. So correct option is option B. So I hope this is clear to everyone. Now we move to question number 12. So question number 12 says, when a weight of 2 kg suspended from a copper wire of length 2 meter and diameter 0.2 mm, its length increases by 8 mm. If the diameter of the wire is doubled, then the extension in its length will be. So again this question is similar. So this is a wire that is suspended by some weight, and this is 2 kg. Suppose this is the small l and this is capital L. So we know y is F by A divided by small l by capital L. So y is F capital L by LA. So small l, that is length, will be F L divided by A Y. So here the weight is 2 kg suspended from a copper of length 2 meter, diameter 0.2 meter. Its length increases by 8 mm. The diameter of the wire is doubled. So the diameter of the wire is doubled, then the extension in its length will be. So when the diameter is doubled, then what will be the change in length? So again L prime will be, F is same, the length of the wire is also same, divided by, this is, so f prime L prime divided by a prime y prime. So this is what, this will be the L prime. So f prime is f, L prime is L, and y prime is y. A is getting changed, so a prime will be, so here the diameter of the wire is doubled. So when diameter is doubled, diameter doubled, so r prime will be 2r. So r prime square will be 4r square. So a prime will be 4a. It will be 4a. So 1 by 4 fl by ya. So this FLYA is nothing but the old, the earlier elongation, which is 8 mm. So 1 by 4 into small l, that is 1 by 4 into 8, 2 mm. So L prime will be 2 mm when the diameter is doubled. So I hope this is clear to everyone. So with this we come to the question number 13. Question number 13 says, a force A produces an extension of 4 mm in a thread of radius r. Now if the force is made 4f and the radius is made 4r and all other things remaining same, the extension will become 1 mm, 2 mm, option C 4 mm, or option D 0.5 mm. Again this is similar. So we know L is f L by ay. So L prime will be 4f L by 16 ay, because a prime is 16a and f prime is 4f, because r prime is 4r. So a prime will be 4 square r square, so 16 r square, so 16 a prime, it's 16a. So it will be 1 by 4 fl by ay. So 1 by 4 into fl by ay is 4 mm, that is the older elongation. So L prime will be 1 by 4 into 4, 1 mm. So the correct option is option A, 1 mm. So all these questions are almost similar to each other, but the variables are different that we want to find in the question. So this was the last problem of today's introduction session. So I thank you all for joining in this course. So I hope this problems that I have been solving in this introduction session will be helping you in the preparation of your exam. With this, we come to the end of today's introduction session. That's it from my side. Have a good night.